In the last couple of videos, we've been looking at examples of how we can use eigenfunctions of differential operators to obtain the solutions of differential equations. We're going to do another example here in this video, but this is going to be a physical example. There'll be no new mathematics per se, but I want to illustrate the process within the context of a physical application. The application is beam column buckling, so either a horizontal beam or a vertical column. Let me just set this up by contrasting the discrete systems that we considered in Chapter 2 as well as continuous systems, which we're going to look at here. So in discrete systems, we're looking at discrete objects such as springs, masses, pendulums, and so forth. This is what we did in Chapter 2, for example, when looking at the spring mass example in that chapter. Such systems are governed by a finite number of degrees of freedom, which is the minimum number of dependent variables required to fix or specify the state of the system. The equations of motion are ODEs that evolve in time. And when you ask the physical question, is that system stable, the mathematical answer arises in the form of an algebraic eigenproblem, which we dealt with in Chapter 2. So AU is lambda U. Now in continuous systems, we now have continuous objects, so things like strings and beams and membranes and so forth, where the mass is distributed throughout the system. We now have an infinite number of degrees of freedom. They are governed by partial differential equations in both space and time. And then when you ask the physical question, is that continuous system stable, the mathematical answer comes in the form of a differential eigenproblem, such as LU is lambda U, which of course is the subject of this chapter. So we're going to look here at a continuous system, a beam or a column, and we're going to look at its stability, more specifically its buckling stability. So here is the equation that governs the buckling of a beam or a column. This is the stability equation. So it's derived in the variational methods book. The reference is given here. I'm just going to start with the governing equation. But again, this is not the equation for the stresses or strains, for example, in the beam or the column. This is the equation for stability. So the physical question is, if I perturb the system slightly, so if I take my beam or column and I give it just a little infinitesimally small nudge in the lateral direction, the question is that going to become unstable and therefore buckle laterally, so a large scale buckled motion. So again, here is the governing equation. It's a fourth order equation for V. V of x is the buckled distribution, the lateral distribution of the beam, in this case, as I've drawn it here. E and I. E is a property of the material, it's Young's modulus, and I is the moment of inertia of the cross-section of the beam. The product of the two, E times I, represents the stiffness of the beam, so how stiff is the beam to bending moments. P then is the compressive force acting on the beam or the column. So as we increase the compressive force P, how much do we need to do so before it buckles, before it becomes unstable? That's the question we want to answer. Now we need four boundary conditions because it's a fourth order ODE. So let's say x is equal to 0, it's hinged, so that means it can't move laterally, so V is 0, but it also can't withstand a moment. And moments are related to second derivatives, so V itself is 0, and the second derivative is 0 at x is equal to 0. At the left boundary, let's say that the beam is fixed. So in that case, it cannot deflect laterally, so V at x is equal to 1 is 0, and the slope as well is 0 because it's fixed, so the slope has to remain 0. So you can see these are homogeneous, as they must be for differential eigenproblems. So let's assume that our beam has a constant cross-sectional area, has E and I that are both constant. So in that case, they can be taken outside the derivative, and you could group our parameters P over EI together as one. And if we just randomly choose a Greek letter, say lambda, we'll set lambda sub n is equal to P sub n divided by E sub I. Now the subscript n implies that there are several, or many, in fact, infinite numbers of the values of P, which will do something interesting, in this case, buckle. So when we substitute that into our fourth order equation, this is what we have. We have the fourth derivative of the lateral displacement V plus lambda times the second order derivative of V is equal to 0. So we have a fourth order linear constant coefficient differential equation. This is our eigenproblem. It's a differential eigenproblem. So again, the governing equation for stability is a differential eigenproblem. Now in this case, it's what we call a generalized eigenproblem. And that's because if we were to write this in our usual differential operator notation, there would be L1 operating on V is equal to lambda times L2 operating on V. So there's a differential operator here in the lambda term as well as here. So we call that a generalized eigenproblem. There's a corresponding generalized eigenproblem in the algebraic context as well, which is very similar. Now we could simply do a change of variables and say that the second derivative of V with respect to x is a new variable, in which case we'd have a second order differential equation to solve for our eigenproblem. Let's just leave it in fourth order and follow through accordingly. Now because we're looking at a physical problem, we can think about what does it mean physically when certain things happen mathematically in our problem. So for example, if we were to get the trivial solution, which we have always said in this chapter that we don't want, we want the non-trivial solution. So what do the trivial solutions correspond to in the buckling context? Well, if V is equal to 0, that means, of course, that it hasn't buckled. So the lateral displacement is 0, and we're not interested in that case. And the reason is because it has not yet buckled. So when we get trivial solutions for particular values of lambda, that's an unbuckled, therefore stable solution. So what we're looking for are the special values of lambda that correspond to a buckled or an unstable beam. And these occur when we have a non-trivial solution, so a non-zero lateral deflection. And those are the values of lambda correspond to the p's, which are the compressive loads acting on our beam. So that's what we're looking for, is the values of lambda that give us non-trivial versus therefore buckled solutions. All right, so as usual, we can try positive, negative, and 0 values of lambda. Turns out that if you try lambda is equal to 0, that gives you the trivial solution. That actually makes sense. Lambda is equal to 0 means p is equal to 0, and there's no compressive load, so therefore there's no buckling. So that makes sense. If lambda is negative, that actually means that the beam is in tension. And of course, if it's in tension, it's not going to buckle. It's just going to stretch, stretch, stretch. So we're only concerned with cases where lambda is positive, so there is a compressive force acting on the beam or the column. So let's set lambda is equal to plus mu squared, as we usually do, to hardwire the fact that lambda in this case is positive. So you substitute that in, where the solution is of the form v is e to the rx, and we determine the values of r. Now again, there's nothing new mathematically here, so I'm going to go through these steps rather quickly so we can get to the physics, the interesting part of this problem. So we get a fourth order polynomial for r, so we get 4 values of r. We get 0, 0, and plus and minus I times mu. So the double zeros we need to put in 2 terms, but remember when there's a repeated eigenvalue, we need to include an x factor. So we have c1 e to the 0x, which of course is just 1, plus c2 times x times e to the 0x. Of course, the e to the 0x is again just 1, plus a term for the plus I mu and a term for the minus I mu. So that's c1 plus c2x plus c3 sine mu x plus c4 cosine mu x. Again, our rule of thumb is for finite domains, we prefer sines and cosines or trig functions as opposed to exponentials. So we're going to use this form v for the lateral deflection in order to get our eigenfunctions. The eigenfunctions are going to be the deflected shapes of our buckled beam or column. So if we apply the boundary conditions, so v at 0 is 0, that requires that 0 be equal to c1 plus c4, and therefore c1 is equal to minus c4. If the second derivative is equal to 0 at x is equal to 0, then that requires that c4 be 0. So if c4 is 0, then c1 is also 0. Then at the other end, at x is equal to 1, we apply the 2 boundary conditions. V is 0 and v prime is 0, and we get these 2 expressions. So we can, as we did before, we can think of this as 2 equations for the 2 unknowns, c2 and c3. And in order for us to get a non-trivial solution, the determinant of the coefficient matrix has to be 0. So that's 1 and sine mu, and 1 and mu cosine mu, as you see here. So evaluating the determinant, 1 times mu cosine mu minus sine mu times 1 has to be equal to 0. So that we can write as tan mu is equal to mu. That's our characteristic equation. As always, it's a transcendental equation. We expect to have an infinity of roots of our characteristic equation. So let's see what that actually looks like by graphing it. So this straight line here, that's mu. And then these swooping lines, these are tan functions. And so when tan mu is equal to mu, that's where these lines intersect, these curves intersect. And there are an infinity of those values. Now we have to evaluate these intersection points numerically, so I did it in Mathematica. For 0, mu 0 is 0, that of course gives back the trivial solution, which we've already determined is not important, so we exclude that. And then mu 1 is 1.43 pi, mu 2 is 2.46 pi, and so on. And there's an infinity of these values. So then our eigenvalues, which are the squares of the mu's, are 2.05 pi squared, 6.05 pi squared, 12.05 pi squared, and so on. All right, so let's pull together then the eigenfunctions. So if we go back here, here's the general form of our eigenfunctions, but we've determined that C1 and C4 are both 0. So we just have these two terms. So we see that C3 is minus C2 over sine mu. That's from one of our equations in the boundary conditions. And so then V we can write as C2 times the quantity x minus sine of mu times x over sine of mu. And that's true for all positive integer n's. And so again, we have an infinite number of these eigenfunctions, each one corresponding to a lateral buckled shape of our beam. As always, we have our arbitrary constant C2. We can set it equal to 1. We can choose it such that our eigenfunctions are normalized, whatever is convenient. Now let's just think about what would happen if our equation was non-homogeneous. What would that correspond to physically? Well, it actually would correspond physically to if we had lateral forces being applied to our column or beam, and therefore restricting its motion in certain ways. And we'll see why that could be useful in a moment. But let's continue with the case where there's no lateral forces along the length of the beam, just the boundary conditions at the two ends. All right, so we have our values of lambda. We got them numerically. So that corresponds to values of P. The P values are the critical buckling loads. So these are the values of the compressive force P, which will cause each of these buckled shapes to occur. So P1 is lambda 1 times E times I. That's the first critical buckling load, then the second, and the third. So there's an infinity of these critical buckling loads. So in other words, for any P less than P1, we will only get the trivial solution, which corresponds to an unbuckled, therefore zero lateral deflection, beam. Once we reach P is equal to P1, then we get the first buckling mode, V1, the corresponding eigenfunction to that eigenvalue. So here is that critical buckling load. We call that the Euler buckling load. It's the first one that you hit as you increase P. So that's 2.05 times pi squared times whatever the E times I is for our beam. Now the V1, so that's the deflected shape, that's the first eigenmode, is then x minus sine of 1.43 pi x over sine of 1.43 pi. And you can look back and see where those numbers come from. That's V1. So corresponding to lambda 1 is the Euler buckling load P1. Corresponding to that is the first mode shape given here. Now if we plot that, it looks like this. So the buckled shape, the lateral deflection, is a single bulge, as we see here. Now remember, this end is hinged, which is why the shape is able to come in at an angle like this, where at this end it is fixed. So the deflection is 0 on both ends, but here it can't withstand moment, so second derivatives are 0, there's no curvature, whereas here the slope is 0 because it's fixed. Now, if we wanted to achieve higher buckling loads, so if we wanted to achieve P2 or P3 or P4, we would actually have to constrain the lateral motion of the beam or column in order to prevent the first mode or the second mode or the third mode from occurring in order to get the next one. So that would correspond to non-homogeneous right-hand sides of our buckling equation. Now to wrap up this example, what I'd like to do is focus on the mathematical as well as the physical aspects, and show how they correspond to each other. We've mentioned all these along the way, but just to put them in one place and to emphasize the point even more strongly. So the eigenproblem itself, in this case a differential eigenproblem, that governs the stability, in this case buckling, of our beam column. So as always, the algebraic or the differential eigenproblem governs the stability of our discrete, or in this case continuous, system. The values of the eigenvalues themselves, they correspond to the critical buckling loads. The trivial solution, so when the lateral deflection is 0, that corresponds to the stable case when there is no lateral deflection or buckling. The eigenfunctions themselves, so the non-trivial solutions that we get, those correspond to the buckled mode shapes. And when the equation is non-homogeneous, that corresponds to the presence of lateral loads, which constrain the buckling motion of the beam or column.